Bonjour à tous. Donc il est 10h45. On va démarrer. I think I should switch to English because some of you don't speak French at all. We will confirm that later when we have the definitive list, but a priori all the lectures will be in English. So my name is Thomas Salez. I work at the University of Bordeaux and CNRS, and I'm a theoretician in the field of soft matter physics, but with other interests like biological physics, and also I was previously working on cold atom physics. So I know a bit the world of condensed matter physics. So this year is a bit particular, as you all know, but we will make sure that it works very well. I provided you my email in the chat. Most of you already have it through the email exchanges we had yesterday. So feel free to contact me first for feedback on the sessions, what could be improved, because this is really the first time I do that. I just bought the tablet yesterday, so you know we are dealing with a lot of fun now. So feel free to provide me feedback, but also questions on the lectures, on the tutorials, and as well on science and physics in general. Where you will be next year is the most fundamental question for this year. So I encourage you to chat with as many people as you can. All right, so we are going to start. I will probably share my screen first before going to the whiteboard. And feel free to interrupt me at any time. It's better if you speak because I won't be monitoring the chat all the time due to the fact that I will be on the whiteboard. So I hope you can see my screen. And here I have several documents that I provided you in the Dropbox folder. So you must all have access to it now. If this is not the case, again, just send me an email and I will make sure you get everything you need. So in this Dropbox folder for the tutorial number 1, which is today, you have several articles. There is a first one, which is called Complexity Explained, that I encourage you to read. It's very simple. It will give you a broad picture on the novel interest in complexity in science. This is a modern word and a modern field. So have a look at it. It will give you very broad picture. I found it very nicely written. A second article I encourage you to read is an article by Weinberg. So Weinberg is very famous in high energy physics, not at all soft matter, but he is a famous physicist and teacher. And in this very short article, he is providing advices to students about the choices they have to face in deciding which PhD they will perform, and more generally, which type of research they want to do. Mainstream or fashionable, but at the same time, you can also explore some pretty novel things. So just have a read, it's nicely written. And finally, today we will be dealing with, let me move something. We will be dealing with polymer physics, and in particular, we will start by very simple results on the shape and statistical conformations of polymer chains. And therefore, I gave you an article, which is a kind of review article by Carlos Bustamante, as you can see here. And it's basically how the knowledge about the statistical physics of polymers will help you do some quantitative things in biology. For instance, with DNA, if you pull on a DNA, a single molecule of DNA, and you are recording some force displacement law, for instance, well, you might be able to infer a lot of information about what's going on inside. So have a look at it as well. And finally, I tend typically to present you books at every lecture. So the book of today is the following one. It is called Soft Condensed Matter, and it's a book by Richard Jones. And it's a very, very broad introduction on soft matter. So you won't find technical details in it, but you have the big picture. Several different fields ranging from colloids and polymers to droplets, for instance, and you can already have a glance of what's going on in soft matter. So note this down. I unfortunately cannot give it to you physically. All right, so finally in the Dropbox folder, you will find all the tutorials. So I would like you to prepare them in advance so that we are discussing during the lecture. So here is the first one, the one of today, where we are dealing with polymers. So please open it, and we are going to discuss it now, and I will switch to the whiteboard. Before that, do you have any question currently? Apparently not. Let me look at the chat. All right, so everyone is with me. And so we are going to start now with the whiteboard. All right, so hopefully you can all see the whiteboard that I will be using for the first time of my life. Kiddingly, I tried yesterday already. So in the lecture of today, we are dealing with polymers. A polymer is a long assembly of monomers, so it's a very large molecule, and typically we will be considering a linear chain. So for instance, something which is like that, okay? So this is a very long molecule which is linear, and it's made of an assembly of units, right? So to model that, we will in fact do something more precise. We will consider that we have an assembly of freely connected rods, all right? So something like that. And sorry for the handwriting, I need to adapt. Right, so basically you have an origin here. You have a first monomer, a second monomer, a third monomer. Let's continue the list with the I monomer. And at the end, you end up with a number of monomers, which is not on this drawing, but in reality, a number that is much bigger than 1. Okay, so you have a huge amount of monomers, typically 1 million. In addition to that, we assume that this system is placed in a 3D world, right? So we are working in 3 dimensions for now. And we will assume also that this polymer chain lives in a solvent at temperature T, for instance, for now. But we will neglect any effect of the solvent apart from that. And finally, each bond here can be mathematically described by a vector. So R1 for bond number 1. You can go to here, for instance, R3 for bond number 3. And Ri for bond number I, right? And so on and so forth. The important thing that I want you to realize for this very simplified model is that first, all those bonds will be taken as completely independent. They will fluctuate completely freely, so they can even overlap. There is no problem with that. They are independent objects, so they are random due to the thermal fluctuations. And finally, we assume that their length is fixed, so they cannot extend like real molecules. For now, they will be rigidly fixed to a certain value in terms of norm. So we will assume that whatever monomer we are considering, the typical extent will be given by a number A, which is basically of nanometric order of magnitude, right? So with all that, we will introduce 2 main observables. The first one is the probability of the orientation of one bond. So I call it small r, but of course it's Ri, whatever I you are taking. So this is something we have to describe first. And from that, we would like to calculate at the end the probability of having the total extent of the chain, capital R, that I will define in a minute, as a function as well of the number of monomer units. Okay, so this will be the main observable that we want to derive at the end of the lecture and do some applications with it. So what is capital R? Well, let me open another page here. Capital R will be simply the sum of all the monomer vectors. So basically, in the picture I provided before, where you have a certain polymer chain, well, let me switch colors if I can with this tool. Basically, this is this quantity. It's the vector connecting the origin to the final point, if this is the origin. All right, so we want to know the statistics of that, provided the fact that we will know the statistics for every monomer units, right? Okay, so we will, in this tutorial, first start by describing very simple scaling and symmetry properties of this problem. And then we will formally calculate the probability of finding capital R, the main vector, the end-to-end vector. And then we will do some applications with that. All right? So if it's okay for everyone, we will start now with the tutorial. So let me change gears. And now we are dealing with part 1 and item number 1. So first of all, we want to estimate or precisely calculate, in fact, the probability of finding a certain orientation for one monomer. Small p, probability of finding R. So we've said so far that we have independent monomers. So each monomer is free to rotate completely in all directions with equal probabilities. It's an isotropic problem. So we know from that feature that P of R is in fact only a function of the norm. And I will note down the norm as simply, by definition, R. So we know it's a function of the norm only and not the orientation. And moreover, we know that we have bounds that are rigidly fixed to a certain distance, small a. So as a consequence, we know that this has to be proportional to a delta function with R minus a here. So that we are sure that the distance R is fixed to the value I provided before. All right, so the question is, what is the value of A? Well, we have to know that the probability is normalized. So the integral over 3D space of P has to be 1. This is the criterion. And therefore, if I express the integral in spherical coordinates, well, we have element of distance, element of angle, element of other angle. We have a sine theta, we have capital A, and the function delta of R minus A. And this altogether has to be equal to 1. So it provides me immediately, you can see that the phi integral is obvious. The theta integral is also obvious. So you have a 4 pi, which is the solid angle in 3D, times A, the constant. And then you have to do the integral over R. But the integral over R is immediate. You get, sorry, I was forgetting something here, which is R squared. So you get A squared equals 1. And therefore, your probability is obviously of the type the Dirac function with the proper normalization. All right, so we know in this very simplified model the probability for an elementary bond to be selected. All right, so now from that we would like to calculate the main probability. So let me play a bit with this quantity first. What is the average total extent of the polymer chain in terms of vectors? So I introduced R before, so we are interested in this quantity. This quantity is simply the average of the proper definition that I gave you before, the sum of all the individual orientations of the monomers. And by linearity of the sum and the average operations, we can simply invert the two, and we end up with the following expression. Right, so we are led to calculate this, and we know that all the monomers are equivalent, they are identical. So basically we can drop the I here, and this is simply n times the same quantity that we want to calculate, the orientation on average of one vector. So physically, we expect that object to be a 0 vector, because the orientation in this way for a monomer or this way are totally equiprobable due to the fact that we have an isotropic problem here. Therefore, we know that the result should be 0. We can, because we are beginning slowly the tutorial, we can do it as an example, and then we won't do those types of calculations again. All right, so how to define that? Well, we can go again to the definition of the average. So the average will be the integral over the vector R, sorry for the handwriting, against the distribution that we identified above, and then the vector R. And then we can go to spherical coordinates, for instance. And in spherical coordinates, we have n times the triple integral d of R squared, I should not forget it this time, d theta, sine theta, d phi. And then we have the probability that we exhibited just before, and the vector R. And the vector R, I can write it as a vector. We have the norm R cos theta here. We have R sine theta sine phi for the y-axis, and for the x-axis we have r sine theta cos phi. All right. So we don't have to do much calculations here. First of all, you immediately let me change gears, if I can show you. Yes, up. So you immediately see that here we have a cos phi, and for this line there is no other phi dependency. And since we are integrating phi from 0 to 2 pi, this means immediately that we get 0 for this part of the integral. So this provides 0. It will be the same for that guy. And here we have a cos theta times sine theta. So it's sine 2 theta, if you wish, by trigonometric relations, apart from a prefactor. And therefore, again, since theta is integrated between 0 and pi, we can make sure that this is 0. So you see, all those statements can be very quickly verified. So I won't do it all time. I will leave it to you for homework. All right, so let's continue and now go to another interesting quantity. So now this is point 3. Since the vector is not very meaningful, the meaningful quantity is the next moment of the distribution, and this is the RMS value, if you wish, or the variance if you take the square. So we are interested in the following quantity. We call it R0, and it will be the average of vector R squared, so the norm squared, with the square root. So this will give you the typical extent. So this is meaningful, right? It won't be 0 for sure. So let's again recall what R or R square is. Well, we know that this is the sum of all the individual orientations, as we already explained. Now it's a scalar product, so we have another one, which is exactly the same. All right, so we are dealing with this square, and so this can be written like the sum over I and j. I don't put the bounds anymore, they are obvious, times this product in terms of scalar product. All right, and we want the average of that. So the average of R squared will be the average of the previous quantity, but by linearity, we can invert the two linear operations here, and so we end up with a sum of averages. All right, so now we can separate this quantity into two terms. There is a term which is the diagonal one, if you consider it as a matrix, which is the sum over I of the R I squared, if j equals I. Then there is another term, which is the one where you have different indices, where you have Ri times Rj. All right. And we have to remember one hypothesis of the model. Here we are dealing with independent bounds. Therefore, the average of the product has to be the product of the averages. So this boils down to the product of Ri times Rj by independence. Let me take the spotlight here. Oh, sorry about that. And so we already demonstrated that those guys, they should be 0 due to the isotropy. Therefore, we are left with calculating the first term only. All right. Again, this will be n times the norm of one monomer. And then we can do exactly the same type of calculations I've provided you before, but it is obviously this guy. So the final result that is important for you to remember is that the typical extent, the end-to-end distance of your polymer chain is of the type square root of the number of objects times the size of an elementary object. And this is an important result. It's already telling you that we are dealing with a diffusive-like process. If the number of objects is considered as time, the extent will be proportional to the square root of time. All right, so we have to remember this feature, and I'm sure you already are familiar with that. So we can just quickly do an estimate of that. So let's take a typical polystyrene chain with, let's say, 10,000 units. So we can say that we have 10,000 units in a row. And typically for polystyrene, for instance, you have units that are of the, let's say, angstrom towards nanometer range. So I can take, for instance, 2 angstrom, which is pretty reasonable. So therefore, you immediately see that R0 will be approximated by the square root of 10 to the 4, which is 10 to the 2. And then we have 2 angstrom, which is 2 10 minus 10. So we are dealing with something which is 20 nanometers. All right, so it's already giving you some information. Your polymer chain that you synthesized as a chemist is there, and its typical extent is 20 nanometers. So it seems that your molecule, your elementary unit in your polymer solution, for instance, this object has a nanometric range, but 10 nanometric here. So it's a large molecule. So you are immediately seeing one aspect of soft matter is that you have an intermediate length scale, which is mesoscopic. It's a huge object. More interestingly, with the current technologies and with the current knowledge, we are able to address nanophysics, right? And we are able to prepare and measure samples in this range. We are, for instance, able to fabricate nanofilms of polymers that are of 10 nanometric range, let's say. So therefore, you are creating systems whose typical sizes are comparable to the sizes of the inner constituents. So you are really not in a 3D world anymore. You are in a confined world, and we expect plenty of novel properties to emerge from that. All right? Okay, so let's continue with the first ideas there. We want to estimate the volume fraction, which is typically occupied by the chain when it is in a solution. Okay, so again, you have a certain polymer chain that has this shape in 3D. Then we already calculated that the typical extent here is a sphere with a radius R0. Okay, this is the typical extent. However, this chain is doing a random walk. It's like a diffusive process, and so there is plenty of vacuum here. Vacuum is, of course, solvent in my context. So the question is, what is the volume fraction really occupied by polymeric material? So to estimate it, I will forget about all the prefactors, but this volume fraction will be simply the volume of all the monomers, so n times the volume of one monomer, divided by the volume of the total chain, which is typically, on average, this guy. So by recalling that R0 is going like the square root of the number of objects, you immediately see that we have something which is like the inverse of the square root of the number of objects. And if you now put numbers, and remember that we have 10,000 units, for instance, well, this is 1%. For instance, you can do much less than that if you increase the length of your polymer. Therefore, you immediately realize that your chain is in fact mostly occupied by everything else, solvent or other polymer chains. If you are now in a dense assembly of polymers, well, you will have plenty of polymer chains that are crossing each other, and you will create a kind of spaghetti noodle plate with plenty of entanglements, so knots between the chains. And this is a key feature of polymeric materials because it will provide some long relaxation times, some viscoelastic behavior, okay? All right, so this is an interesting feature to have in mind. Now, in a typical solution, you will have three big situations. You will have a situation where, and we call that the dilute situation, where your polymer chains are mostly very well separated from each other. Let's say you put a very small quantity of polymer into the solvent, and so you have chains that are separated. So this situation, we will call it very small concentration. Let's say very small with respect to a concentration that we will define in a minute. There is another situation, which is the situation where, in fact, if I, let me change colors, you have plenty of, sorry, with that. You have plenty of other chains that are mixed with each other. And you still have solvent, but all the chains start to really talk to each other and feel the interaction with one another. So in a solution, when this situation is reached, we call that a semi-dilute situation. And this is basically for a concentration which is bigger or largely bigger than C star, if you wish. And finally, there is a situation where you have no solvent anymore. Okay, well, this is a melt. This is what happens if you take your plastic ruler that you use to do straight lines, you make it burn, and it becomes something very viscous. This is a melt of polymer. There is absolutely no solvent anymore. So really the concentration is infinite in that case, or very large. And this is what we call a melt. But here we are dealing with a solution in this description. So what is C star? Well, C star is, let me open another whiteboard. C star is the situation where all your polymer chains are typically, well, of course, those are random arrangements, but on average, you have a perfect paving of space by full polymeric units. They are not too much intricated, they are not too much separated, they just, on average, basically pave space, right? And so this is the critical concentration between the two situations I've described before. And here, for that case, C is comparable to C star, and it provides immediately a scale for C star. C star is the situation where you have n units of monomers inside the volume pervaded by one chain. So basically the concentration will be this one. And this is, as we did before, 1 over the square root of n, there is now a unit. So we can put some orders of magnitude again. So this is approximated by 1 over 10 to the 2, if we take the square root of 10,000 units, and a cube, so you have 2 to the power 3, which is almost 10, and then you have the angstrom to the power 3, which is 10 minus 30. All right, so 10 minus 27, so this is 10 to the 27 meter minus 3. So this is also 10 to the 24 liter minus 3, and 10 to the 24 is 1 mole, okay, if you remember the Avogadro number apart from prefactors. So this is what we will call 1 mole per liter. All right, so you just to have orders of magnitude from chemistry, 1 molar, it will be the typical concentration around which you start to feel entanglements or at least interactions between polymer chains. All right, so let me move now to the second part. A really important feature of polymeric statistics is that you have scale invariance, meaning that if you take a small ensemble of units, you will have the properties that are exactly the same that if you would take the ensemble of the chain. So there is a scale invariance, of course, in some window above the microscopic molecular size and below the total sample length. But in between, you have this type of feature. So let's just go through very quick arguments for that. So we again want to understand what is the root mean square distance between two units. So now we are dealing with a polymer chain here, and we, for instance, identify one monomer, let's call it I, and another monomer which is far away here on my drawing, which is called J. So we can define, as before, the end-to-end vector for this object, right? It's called R of I and J. Question, what are the moments of this one? Well, the first moment will be 0 by isotropy again. And so the next one is the variance that I'm interested in. So here we will have something like a sum over M of small monomeric units as before. And we will start at I plus 1 and end up at J. So this is exactly what we did before. We are summing all the little monomeric units from the beginning to the end. Now, if we are interested in this quantity squared, well then, as before, we will have a sum over M and let me introduce another index. And we will have, as before, the average of the scalar product of each monomeric unit here. Again, only the diagonal term will matter, and so we will end up with Rm squared. Rm squared being equal to A, U to A squared, we end up with J minus I. If we remember the bounds of the integral here, this is going from I plus 1 to J. So the total number of items is J minus I times A squared. Okay, and so again, we end up with the fact that the square root of that, which is the typical distance, average RMS for root mean square distance, will be given by the square root of the number of objects. It's a diffusive process, but it's also here locally. So no matter where is the beginning and where is the end, as soon as you are inside this polymer chains, you have that property at any scale. It's a fractal object. All right. Now from that, we would like to estimate the number of objects of monomers that are present within a sphere or radius B. So again, let me draw my favorite polymer chain here. And let's, for instance, mentally construct a sphere at this point and ask the question. So this sphere has a certain radius B that I can fix at any value I want. And the question, I would like to estimate how many monomers will I find into this sphere. So I'm just drawing the sphere and I'm asking what is the typical number. Well, from the previous slide, you see here that we are saying that the numbers with a square root will be correlated with the size of the object. So this will be B, the size of a sphere, provided you know the monomeric unit here. All right, so let me express this fact. Square root of B times A will be, no, sorry, let me untype. Let me call G the number of objects, and G will be provided by the square of the size on the monomeric size, everything to the square. If you take two limits, you can take, for instance, a choice where B goes to 1, to A here. Well, this is if you take as a sphere simply one monomer. Well, of course, the number of monomers inside this is one monomer. So you get G is 1. If again, now you take the limit where B tends to R naught, which is the full size of the polymer chain. So you take a big volume, including everyone. Well, R naught, you remember that it is square root of N times the monomeric size. And so you end up with G equals N. Okay, so you recover the two obvious limits. No problem with that. All right, so let me now go to the next question and address the minimum number of spheres to pave the way. First, I think I forgot a little point. I can also calculate what is the typical volume fraction associated with this guy. So the volume fraction is the number of units you find in the sphere. So it's G times their volume, A cubed, divided by the volume of the sphere you are considering. So this could be called phi B to distinguish from the previous one. And so you immediately see that it goes like with A over B. Again, with the proper limits. So you can also calculate the volume fraction inside this small subunit of size B. All right, so let me now go to the next question, which is to try to estimate the minimum number that you would need if you wanted to pave the full polymer chain with spheres. So let me again take a random realization of this process, and let's cover it with an ensemble very coarsely. I'm just doing very coarse arguments here of spheres. Okay, so I'm just covering minimally the entire object with spheres. And the question is, what is the minimum number of such spheres do I need if I want to really cover minimally the polymer chain? Well, there is something which is conserved, which is matter. So the total number of objects must be constant. So we know that n, total number of monomers, should be retrieved in this configuration. And in this type of paving, you will have a certain number of units that we can call NB, the minimum number of units that allows you to cover the full chain, times the number of monomers inside one unit, so times G. Right? And so in the previous calculation, we estimated G to be B squared over A squared. So you end up with NB. And this, sorry about that, this is, since I'm keeping only scalings here, I will put that number because G is already in scaling, but it's an equality. NB will be provided by N divided by B squared times A squared. And if now you realize that N times A squared is nothing else than R naught squared, as before, well, you end up with the following fact, that R naught is given by the square root of NB times B. Remember that before, the result was that it was square root of N times A. A is the real monomeric length. Capital N is the real number of objects. But now we have kind of grouped them into bigger spheres of size B. And there is a certain number of those spheres, which again has a square root here. So you see there is a self-similar property. No matter the way you group the units together to form artificially bigger monomers, but again, this artificial polymer chain or renormalized polymer chain will have the same properties. Okay, so finally, according to you, what would be the limitations of such a modeling? Does anyone has an idea here? Feel free to open your mic if you can. Well, I assume it's difficult with Zoom, so we will improve that interaction in the future. So basically, what I've described here is a fractal-like property, a fractal-like or self-similar description of the polymer chain. There are limitations. Of course, this picture doesn't hold if I'm looking at sizes that are comparable to the monomer size. So the size I'm looking at, let me write it very coarsely, size must be much bigger than the atomic or molecular unit size. Otherwise, we enter in another world, which has nothing to do with polymer physics. Again, there is nothing beyond the sample size or beyond here the full length of the polymer chain. So this picture will be valid only in a range of sizes, typically the square root of the variance that I was describing before, in between the monomeric size and the macroscopic macromolecular size. All right, so those were really preliminary elements before we move now to the exact calculation that we are interested with. So if there are no questions, let me just quickly monitor the chat. I guess you are all with me now, so we will go on. With now the third and fourth part. All right, so we are now at part number 3, if you take your tutorial here. All right. And part number 3 is really about calculating the object, the distribution, and not anymore only the first and second moments, but the full distribution of the end-to-end vector. So to do that, we will first rely on the Markovian hypothesis that I will rederive for you here, and which might be known from those of you who did some mathematical probability theory already. All right, so we want to express the probability of going from the origin to the total extent of the chain in a certain number of units. And to do that, what we would like to convince you of is that to go from one point to the final point in a certain configuration, you first need to go in a smaller number of units to a point, and then from that intermediate unit, finish the process. So it's, if I write it again with a certain polymer realization here, I start at the origin and I first end up at some intermediate point R prime. This is the origin. Of course, this required a certain number of units. Let me call it n. N will be here something which is in between 0 and the total number of objects. And finally, I will end up here with my end-to-end vector with the total number of units. And the probability of getting the full extent is the probability of going somewhere and then finishing the process and integrate over the position of that somewhere, because they are all possible. For a certain distance, the chain could really go this way or could really take another path and go this way. And we have to integrate over all possibilities. So in that sense, we will write the Markovian hypothesis this way. We will say that the probability to go from the origin to a certain extent in a certain number of steps, it will be the probability to go from the origin to an intermediate point and then finish the process. And where it's Markovian, it's because we assume that the future doesn't depend on the past. The monomers are independent, as I told you before. So if you have independent processes, you will multiply the probabilities. And so it will be multiplied by the probability to finish the process, meaning go from the intermediate point to the final one. And of course, you cannot use the number of units you want. You have to use the remaining number, which is n minus n. And I told you that R prime doesn't play any role. It's an intermediate point, and it can be anywhere. What matters is the total extent. So you have to integrate in 3D, let's say, over this intermediate point. And this result should be true whatever the intermediate step you want to consider. To go from 0 to monomer number 100, you have to go from 0 to monomer number 3. It's necessary, and this 3 can be anywhere. But you can also say that you go from 0 to monomer number 15, and then from 15 to the rest. Whatever intermediate point you choose, you should integrate over the position of that intermediate point. And this is the key equation that will be describing the statistics of your polymer chain. All right? What we want to do is not to stop here, but we would like to make some approximations. In particular, assume that now we don't have a finite number of units, but we have an infinite number of units. It's an infinitely long polymer chain. You can think about the thermodynamical limit if you think about statistical physics here. And if we do so, we will also assume that the size of the monomeric unit is going to 0. And we will conserve the typical extent, okay, in this limiting process. Therefore, we will be able to transform this fundamental Markovian identity into a partial differential equation on P, a continuous description here, and we will be able to solve it. Right? This is the plan for now. So before going to that, let us consider two specific values here, or points. So this is the next question, and we are interested in estimating P of R and 0. So if you look at the tutorial, we want to know this guy. So stated with words, what is the probability of finding an extension of the polymer which is a vector R in 0 step? Well, if this extent is finite, the probability is 0. There is no way you can go somewhere without having at least one step. So again, you are pretty sure that the only result that you can have is that you have a Dirac distribution. All right. I take a Dirac because I want the integral of the probability to be 1. All right. So it's a normalized distribution. You can check that in the Markovian identity before. Let me remind you. So let's use the Markovian identity by replacing capital N by 0. If you go here, there was this capital N, and I will just put it to 0. It will be 0 here, and thus N as well as to be 0 due to the fact that N is in between 0 and capital N. All right. So now I write the Markovian identity. I need to integrate the process over an intermediate point, R prime. Then I take the probability of reaching R prime in 0 units. And then I finish the process, well, in 0 units, okay? But then if I plug this object inside the previous expression, you immediately see that it's self-consistent. Here, for instance, this is delta of R prime. So if this is delta of R prime, and if you integrate over R prime, well, you are pretty sure that R prime goes to 0, and thus it leads you to P of R and 0, which is precisely the left-hand side. So you have really an identity that works, and it's satisfying because this is what you would expect. All right, it's a simple fact. Another important point that we need to think about is that what is the probability of reaching the end-to-end distance in one step? So you start at the origin and you want to know what is the probability of finding the total distance at one step. Well, if you have only one monomer in a row, this is the elementary probability for the orientation of one monomer. So it's the small p that we introduced before at the beginning of this tutorial. Of course, it is estimated for capital R. Okay, so we know it. It's delta of the norm of R minus A divided by 4 pi A squared. We've calculated it. Okay, so we know a certain number of facts, let's say of initial conditions, you could say, to start the solving. So here, I would like to expand. So let me just change that. All right. So this is part 3. I would like to expand P near capital R, but by removing one monomeric unit, okay, with the vector here. So I would like to assume that the monomeric unit is very small in size compared to the total polymer chain. Again, I have in mind a continuous limit where the number of monomers will go to infinity. And so I want to do a Taylor expansion to have some derivatives appearing in order to introduce a partial differential equation based on the Markovian identity. This is my goal. So Taylor expansion is easy to perform. Here, remember that we are in 3D, so this is a vectorial form of the Taylor expansion, but this is the same. So we have the point at the origin without the small r. Then we have the linear term, which is minus r times the derivative. In vectorial representation, this will be the scalar grad operator applied to P, but then estimated at the origin, like for a Taylor expansion in one dimension. And then you have the second order term. The second order term, there is a 1/2 factorial appearing, and there is r squared. So here it's 2 times this operator. So the operator r scalar nabla to the square applied again to P, evaluated at the end at the origin, and etc. You could go to third, fourth order, and so on. But we will limit ourselves to the second one, and this will become clear in a minute. You can also rewrite this with summation notations. So the scalar product will be the sum over, let's say, an index that says that if you are on x-axis, y-axis, or z-axis, so you have the spatial index here between 1 and 3, and you are integrating r alpha, which is the coordinate, so x, y, or z, and then you have the derivative over alpha applied to p, again at the end evaluated on r and n, plus 1/2, and then you have the same. You're summing this time over two indices, alpha and beta, and then you have d alpha, d beta of p, and I'm missing something here. R alpha, R beta, d alpha, d beta, p. And I don't write the dependencies, but it's R and N. Okay, so this is the same expression. And I will stop at the second order now. All right, this is my main expansion. And then I would like to be able to invoke the Markovian identity. Let me remind you the Markovian identity. It is here. So I would like to connect the total probability from going to the origin to R to some intermediate probability. Stated differently, I need to find this integral somewhere of having the probability from the origin to one point in a certain number of units, and then from that go to another point and integrate over the intermediate point. So in order to use that, the idea here will be to multiply the identity I just derived by the probability of doing one step. So that if I integrate the whole, I will have a derivative with respect to the step, which is the equivalent of time in my language. So let me be more clear by doing it in front of you. So I'm here at question number question number 4. So I will take another note. So we are simply taking this equation that we called star, and we will integrate star after a multiplication by P of R. This is the probability of moving by 1 unit. Okay, more. So it says that on the right hand side you have the integral over P of R, sorry, the left hand side, minus R prime or R in n units, and now I have to multiply by small p of R, and I integrate over this intermediate point here, R. On the other side, I remind you that I had P of R and N. Well, it is also multiplied by small p of small r. Then I have the linear term, and so if we go here, the linear term is minus times the sum that you see here. So I forgot to say something. I need to say to you, d alpha, but you must all be familiar with that already. It's simply the derivative with respect to the coordinate r alpha. Okay, it's an Abla operator. I take the capital R here because I'm estimated at the end everything at the final point. All right, so here I have minus the sum over alpha. And here we have to see that there is this d alpha p of R and N. So I take this is what I had so far, as I have small p of R and the integral. And let me remove my screen here, so that I have more space on my screen. And then I have another term, which is 1/2. And then you have the sum over alpha and beta. Again, you have R alpha, R beta, and you have the D alpha, D beta of capital P. And everything is multiplied by small p of R, integrated over the R. All right? So let us think a bit. Let me look at the left-hand side for now. So on the left-hand side, you have the probability to go from the origin to R minus R, and then you complete the process by this guy. And this guy, we've demonstrated before that it is in fact the probability of going to small r in one step. That's what we wrote here. Okay? So I'm just replacing small p by capital P with 1 unit. And now you see that this is the Markovian identity, because we are going from 0 to small r in 1 unit, and then we are going from small r to r in n units. So altogether, this is the probability of going to capital R in n plus 1 units. And now you understand why I have done this multiplication. I can make use of the Markovian hypothesis here. All right, so what about this one? The second term, well, you see that this is not depending on small r at all. So I can put that guy outside the integral, and therefore I end up with p of r and n times the integral of small p. But the integral of small p is 1 because we have a normalized probability. Then, if you understand my process, I have the sum over alpha. Again, the derivative with respect to alpha doesn't depend on small r, so I can put it outside the integral, and I end up with times the average of r alpha. And then, for the final term, I have my double sum with the derivative with respect to alpha and the derivative with respect to beta of p, and then I have the average of r alpha, r beta. No more integral. I've made use of the Markovian identity to produce that. Okay, so what is interesting first is that, let me change colors here. I can put that on that side, and you see that there is a differential operator that is appearing. There is n plus 1 and there is n. So in a sense, we have a differential with respect to n that is appearing. So here now we have the n derivative with respect to n of p of r. Of course, you might argue about the fact that, well, n is a discrete object. It's an integer, and we are derivating with respect to an integer, which is something a bit weird. But I remind you that we are considering a limit where n goes to infinity, and where the size of one monomer is going to 0. So in fact, we are reaching a continuous description. We call that the Brownian description. And this is perfectly well established mathematically. I'm just using physical notations here. All right, what about this guy? This guy is the average of the coordinate, let's say x of one monomer. So you have one monomer unit, which has a certain orientation, and you look at the average of the coordinate along an axis, x. Well, the average of that value, as we already explained before, is 0 because you have as many chances to be like that than to be like that. Okay, so we already calculated that. This has to be strictly 0. Remains to estimate that quantity. So we want to quickly understand what this value is. And we will first place ourselves in a situation where alpha is different from beta. So for instance, example, this is x times y that you want to calculate here. Okay, so in spherical coordinates, this will be r squared, or let me do it slowly. There is a sine theta, there is a cos phi, and then this is multiplied by the same, but with the other projection here. Okay, so this is basically, remember that r is fixed to a squared, so this is sine theta squared times cos phi times sine phi. And the average is not a uniform distribution behind. This is integrated against the probability of orientation small p, okay? So if you want to express that, well, it will be simply d theta, d phi, dr. You have r squared sine theta. You have the probability distribution, which is here. And then finally, you have these angular dependencies. And a square is now gone, okay? So no matter the r dependencies, what we see here is that, let me change color, up. Here, this is proportional to sine 2 phi. Careful, the alpha here is not the same alpha as before. It just means proportional. Sine 2 phi, remember that phi is integrated between 0 and 2 pi. So clearly, this will be going over 2 periods, and so this is 0. There is no need to calculate anything more. So we are showing that basically the correlator between two independent orientation is 0. Well, this is just because we are dealing with an object that is isotropic with independent problems for each direction. So it will be the same for x, z, zy. So you don't have to work more to do that. This will be 0 if alpha is different from beta. So in this expression here, the only important part here is when alpha is equal to beta. So we can now write again. Sorry, so I have no more blackboard. So I will save that and clear all drawings. All right, so we will now start again from, sorry, I'm learning in front of you how to use this tablet and Zoom. All right, so all right. So now we want to apply what I just explained about the correlator between two different regions. So coordinates. So now we have dn of p evaluated at r and n, which is equal to 0. That was the first term in my calculation. And there is only the 1/2 sum over alpha. Now beta must be equal to alpha, otherwise you have a 0 result. And then you have d alpha squared of p calculated at r and n multiplied by the average of r alpha squared. So now remains to estimate what is r alpha, and I have to remind you that this guy is equal to a squared, right? Because we know that the bond length, the total bond length, is a. But we know also that r squared is equal to the sum over alphas of r alpha squared. Therefore, if I average this guy, here this is 3 times the average of, let's say, 1 alpha naught, a particular one squared. So I immediately end up with the fact that this is a squared divided by 3. This is true in 3 dimensions. If I would go in d dimension, this would be replaced by a d. So all together, I end up with the following equation. dn of p is equal to 1/6 a squared times the Laplacian operator on p. Remember the hypothesis, r is going to 0, n is going to infinity, but we made sure that the typical extent of the chain is preserved in this limit. In addition to that, we have a boundary condition, an initial condition, and we say that P of R and 0 units is delta of R. So now we just make a stop here, and we realize that we have a diffusion problem. To realize that, we just do the following mapping, and we say that time is equal to n times a squared. A diffusion coefficient is equal to 1/6. The position, well, is still maintained. And the probability of R is my field. Is probability of R and N. Okay, so this is just a lexicon. And so if you do so, you end up with the following equation on P, which is the diffusion coefficient times the Laplacian of P in space. So it's really the diffusion equation. And so together with that, we have the fact that we start with a probability or a concentration that is at, so at 0, which is a Dirac. So basically, our problem is to take a glass full of water, put some ink, a really Dirac distributed ink point, and then we look at the relaxation under a diffusive process. And this will be mapped to our polymer problem. All right, so now the next step is to solve that. So we want to solve the diffusion equation. And there I will probably remind you something you already know. But I do it so that those of you who never did this calculation can be on the same grounds, on the same page. All right, so let's go first to one dimension, 1D. And let's consider the following problem. We are dealing with a certain, so this is dimension, so that we don't confuse with capital D. This is the second derivative with respect to variable x for space. We want to solve that with f of x and 0, which is delta. To solve that, there are plenty of techniques. We can simply go to the Fourier space and introduce the Fourier transform. Let me put a hat to distinguish it. And it's only a spatial Fourier transform. So it's simply the integral of your field against x. All right, so the second derivative of f is immediate. We get now the previous equation here. That is this guy. Here you have minus k squared times d, and then f. All right, and delta hat, so the Fourier transform of the initial condition is 1. In Fourier space, a Dirac is 1. It's a flat signal. All right, so we want to solve that. Well, it's pretty easy because now we only have a linear ordinary differential equation, so we can integrate through time. It gives you an exponential. F of k and t is f of k and 0 times exponential minus k squared dt. And f of k and 0, well, is exactly 1. This is 1. We just wrote it. So f hat is basically only this exponential term. So we know the Fourier transform of the solution, the spatial Fourier transform of the solution. All right, and now we want to do the inversion of that. All right, so the real signal field will be the inverse Fourier transform. So by my specific choice of conventions, I need to have 2 pi here now. I take the stuff I just obtained, and I don't need to forget this guy with a -1 due to the convention. And this is, sorry about that, this is the inverse Fourier transform in 1D. So I'm dealing with the integral over R of exponential minus k squared dt exponential minus ikx, and I integrate over k. So here I can really notice that I have k here, I have k here, and so basically it looks like an identity, okay? A plus b to the square. So I can just complete the identity and make a change of variable, okay? So what I do typically is that I introduce capital K, which is square root of dt times k, and I add to it plus I, so there should be a x, there should be a 2 square root of dt to compensate. So that k squared is really equal to dt k squared plus I kx in the cross term minus x squared divided by 4 dt. And what I have here is this, basically. So I just need to complete by adding the third term. All right. Another important fact is that dk, there is only k here, so it's square root of dt dk. All right, so f of x and t, there is this 1 over 2 pi. And now I'm integrating, look at the expression here, the total exponential minus capital K squared, and I need to complete the square and put the proper Jacobian, which is here. So I have 1 over square root of dt, and then I have 1 minus x squared over 4 dt. And remember that this is an integration over k. Now, this guy. All right, this is what I want to calculate. And to calculate that, I simply remove first all the constants here. So this is not integrated because there is no k dependence, so it goes outside. And I'm just led with integrating up over dk. Now careful, the bounds have been shifted. We are in this variable change here. There is I. So we are in the complex plane. Before we were integrating over R along that line. This was small k, but now we are in the complex plane. Then there is a residue theorem that you can apply. You can create a closed contour. The integral on that closed contour will be given by the residue theorem. Here there is absolutely no pole. This is an analytic function that is completely irregular here. And therefore, those parts of the integral, they will vanish exponentially or Gaussianly, I would say. And so you can prove that the integral on that line is equal to the integral on that line. So if you have any question on that, I can provide the details. I think it's not very interesting for our purpose today. So I let you try to do that and come back with questions to me. So all in all, this provides you square root of pi, which is the standard integral of a Gaussian. So I end up with the following result. 1 over, if I group everything, 4 pi dt exponential minus x squared over 4 dt. This is the solution for the diffusion problem in 1D when you start from a Dirac distribution. This is the ink problem in the class. So this is also the Green's function of the diffusion problem, one can show. Now, if you go to 3D, well, in 3D, you have, in 3D, it will be exactly the same, but now you have the probability, which is f, of going from r, from 0 to r at time t, which will be given, well, you have exactly the same. You have square root of 4 pi dt. But now it appears as a factor. So the problem in x, in y, and in z are independent. So you are now multiplying the probability. So you have 3 times the same prefactor. So there was a square root. So there is a 3 and the square root. And there is also this exponential. So it was x here, but you have the same for y and the same for z. So now you end up with the total norm for dt. Okay, so this will remind you something. This is the result in 3D for the diffusion process. This is the Green's function of the heat operator. So remember that now I was not dealing with heat equation, but I was dealing with a polymeric problem. So I have a certain dictionary that is here. So I should transform time into number. I should transform diffusion coefficient into the proper constant and provide you the final result that we are interested in. All right. So for my polymeric problem, back to polymers, the lexicon tells me that P of R and N, well, you have this factor. So now D is equal to 1/6. So there is a 3 over 2 pi a squared. And then you have exponential minus 3r squared over 2n a squared. All right. So this is the solution of the polymeric problem. We are saying that the probability for a certain realization to go from the origin to the end with a certain vector r after n monomers being a large number is a Gaussian probability. That is why in all textbooks about polymer physics, you will hear the term Gaussian chain. It means an ideal description with freely joint monomers, okay? So it's a Gaussian distribution, pretty much like the diffusive problem leads to Gaussian distributions, all right? So now we have the main result, and this is a very idealized model. We will refine it in later tutorials. But we can already work with that to have some feelings. Before doing so, I would like to show you another way of deriving the same result, which is basically a demonstration of the central limit theorem, which is an alternative strategy. So let me do that just quickly and leave you with some homework at the end. So this is, I guess, question number 6. All right. the idea now is can we directly make use of small p of r to derive capital P of r? Well, the probability of going from one point to the final one in a certain number of steps can be subdivided in several probabilities. You need first to shoot for the first bond, then you shoot for the second bond, then the third bond. So actually, since those bonds, they are independent, you have a product of small probabilities, okay? And then you have a constraint. You want that the sum of all these intermediate vector to be equal to capital R, the total length. So you could say that P of R and N is in fact probability of R1. First I shoot the first bond, then I shoot to find the second bond orientation, and so on and so forth until I've shot the last bond. Of course, if I do so, I'm not sure to end up at the correct distance. So I need the constraint, and the constraint is that, let me remove a screen that is in front of my whiteboard. I need to ensure that the sum of all the monomeric unit vector to be equal to what I'm looking for. So there is a constraint. And then, of course, I should integrate over all the intermediate variables. So I integrate over Ri. Okay? And sorry, this is not a triple integral. This is 3 times n integral. So I just write one symbol and it's obvious. All right, so this is really viewing the polymer problem as a central limit-like picture where you have a sum of independent processes which are identical and for which you know the average, you know the root mean square or the variance, and they are all finite and with known values, and so you can a priori compute that. The problem, just formally here, is that you are dealing with a Dirac. So the good space to work on that is either the Laplace space or the Fourier space. This is standard in probability theory. So we will go to Fourier and express the Fourier transform of my field. So it's a Fourier transform over R, which is simply the integral, or it's a triple integral here, over the variable R. Let me take the scalar product between K and R and the real probability of R and N. Okay, I just introduce that quantity. So this is the integral over R, exponential I K R, and then the probability is the integral over all intermediate bound vectors. I put a J not to be confused with the complex imaginary number I. Then you have the product, so I can put it together. You have the product of P of Rj. So it goes in the same product. And then you have IKR, so you have IKR and the delta constraint. And sorry for my handwriting, I must improve that, but it's quite new. All right, so we see here that R should be fixed to that quantity. So I should do the integral over R first, meaning I should invert those two symbols. So I do that, and it gives me the fact that you have the product between 1 and n of the drj prj. And then you have exponential I k times the sum of rj. Okay, and I think I have everything here. And now this term can be transformed into a product as well. So altogether, this gives me a product which has the following form. So p hat, which I'm calculating currently, is the product of n integrals, each one being of the type drj, prj, and we have this exponential I k rj, which is inherited from that. Okay, and here you can see that that j here doesn't play any role. Like I just change names or variables and call it 0, and then rj becomes r. So in fact, we have n times the same integral. It's the integral. So it's a 3, now it's a 3D integral, right? P of r exponential I k r. So it's the Fourier transform of the elementary process to the power the number of objects. And I can just call it I to the power n, where I is this guy. Agreed? So I'm left with calculating I being the integral in 3D space. So I'm going again to spherical coordinates, because that I know that my elementary probability is isotropic. I know everything about it. So dr, d theta, d phi, I have a sine theta and a r squared. Then I have my probability, which is delta r minus a over 4 pi a squared. And then I end up with I, the norm of k, r cos theta. Why so? Because I can always decide how I define my spherical coordinate system, and I can take as a reference, as a vertical, if you wish, line, k, capital K. Here, I'm integrating against another variable, so it's a constant at this stage. All right, so this is straightforward. This is straightforward with the r minus a, so we end up with simply the integral over theta between, remember, 0 and pi, as usual. And then we have the a square that will be compensated. We have 1 over 4 pi, and the integral over phi will give me 2 pi. So I have 2 pi over 4 pi that is remaining, and then I have I k a cos theta. So basically, it is equal to 1 over 2 times the integral over theta between 0 and pi of sine theta exponential I k a cos theta. I k a cos theta, and then I have factor 2, which is okay. So this is really the paramagnetism problem, if you wish. So it's here we recognize the derivative of what is here apart from constant. So it's 1 over 2 pi, 1 over 2, sorry. And then the integral is, there is a minus sign here. There is I k a when I derive between pi and 0. Okay? So it is 1 over ka times exponential ika minus exponential minus ika over 2i, which is a sign. So we end up with the following result. I is equal to the cardinal sign. All right. However, I was not interested in I only. I was interested in p hat, which, remember, was I to the power n. So it is really the cardinal sign of Ka to the power n. You must recognize some diffraction grating pattern here. All right, so if I take the log of P, I can rewrite it this way. So log is the notation for the Neperian logarithm in English. So this is the Neperian logarithm of sine Ka over Ka. Okay, why do I take the log? Well, I take the log because I have in mind now a Taylor expansion. Remember that in all what we are doing now, we are taking the limit where the monomers, I mean, the chain is so large that the monomer units can be viewed as punctual units. So A goes to 0. So if A goes to 0, I can expand the sign because K is one value. It is fixed. It's a real number. And so therefore, I can approximate the log easily, which I can't without the log. So I end up with the logarithm of, well, Ka over Ka. This is the first order of the sign, plus, minus 1 over, so factorial 3, which is 6, Ka squared, or K cubed, sorry, over Ka, plus fourth order term, and on and on. So this is 1. And so you see, I end up with the log of 1 plus something which is small, and plus something which is even smaller. So I will stop here because I will keep only the dominant term in this series. So this is basically minus n over 6 times k squared a squared. And from that result, we end up with what we are interested in, which is the exponential of that, which is p of k. Actually, it's a vector and n a priori, but it only depends on the norm. It's simply the exponential of minus n k squared a squared over 6. This is the Fourier transform of my main observable or field. Okay, the comment that comes here is that it's a Gaussian apart from constant. So the Fourier transform is a Gaussian. We already went through this for the diffusion problem. The inverse Fourier transform of a Gaussian is still a Gaussian. We only have to remember that, so this is written like exponential minus k squared over 2 sigma k squared, where sigma k squared is the variance of that process. And when you do the inverse Fourier transform, it will end up like this time the variable in the real space, not the Fourier space, and you will have the proper variance in the real space. And this variance is simply the inverse of the Fourier variance. Okay, so you end up with the fact that you recover, let me stop here. You recover our result. You recover this guy. Exactly the same. And the prefactor can be properly done if you redo the integral over the complex contour and so on and so forth. But you see, either you go from the Markovian identity and integrate it smartly in a sense in order to be able to transform this into a partial differential equation. It happens to be the diffusion equation that you know very well and for which you know the solution, then that's it. Or you do another strategy. You will remember that the total extent is a sum of all the monomeric extents. And so you go through the central limit procedure. You assume that you have a sum of independent random variables and you are interested in the sum of these random variables. So therefore you go to Fourier space and you do the proper approximation and you get a Gaussian because the central limit theorem tells you that the probability distribution for a quantity that is the sum of many small independent and identical variables will be a normal law. It will be a Gaussian function. All right, so you see with those two approaches, you get the same result. And now you're convinced that for an ideal chain, a chain where all the monomers are independent and freely rotating, you get a Gaussian distribution. So now can we use that result to do something more? Okay. This is the last part. So let me go back to the tutorial. And take the good color for my pen. It's called entropic elasticity. So now we know really the distribution, and we would like to go at the thermodynamic level, consider entropy, free energy, and from that derive the typical forces and try to understand the physics behind all those mathematical details. So the first question is to estimate the entropic cause for elongating a chain. So let's look at the chain, which is like that. It starts from the origin, but it ends up at the origin as well. From this situation towards another situation where the chain starts at the origin, but is fully extended, or at least largely extended, towards a certain distance. So we go from really coming back to the origin to pulling on the chain on one extremity to enlarge the chain, the distance. And so the question is, what is the change of entropy? This has a certain entropy because you have plenty of conformations that allows you to come back at the same point. So you can estimate the number of conformations, and from that number of conformations, you can calculate the entropy. Same in this situation, and so you have a final entropy SF. And therefore, there is an increase of entropy when you go from the left to the right, which is the difference between the two. Question, what is this increase of entropy? Well, the entropy is provided by the probability distribution, if you wish. Up to constant. Because if it's a number, it's not really a probability that enters here. Anyway, we are in the canonical ensemble, and in the canonical ensemble, it happens that the entropy is kb times the logarithm of the partition function. And so we will be all set with that. So in my case, it is pretty clear that the increase of entropy between the two will be the log of P final over P initial. And this without constant. And therefore, kb is the log of, well, in the final situation, I have an extension R, so the probability is to go from 0 to R in n steps, while in the initial configuration, I come back to the origin here. So this is P of being at 0 vector in n steps. And remember finally that P of R and n is provided here. And so it's the probability of being at 0 in n steps times the exponential minus 3r squared over 2na squared. This is just a reminder. So as a consequence, kb log of exponential minus 3r squared over 2na squared. And the log of, it's a Neperian logarithm of an exponential is simply the identity here. So you have minus 3 kb r squared over 2na squared. So you end up with the following result. The entropy decrease when you increase the distance between the origin and the final point is going like r squared. All right. Second point, we would like to calculate the energy increase. So the internal energy increase. However, here we have to remember that we introduced a model where all the bonds are freely rotating. They are free to overlap. So there is actually no interaction. There is no energy in the system. We are only counting the number of conformations or giving the probability for a given conformation. This is related to entropy, but we are not at all integrating the fact that there are forces and interactions between the monomers. This is for later in the course. So for now, there is no energy for a given configuration. Being completely extended or being completely coiled has the same energy for now. So in this very simplified model, there is no internal energy change between this configuration and this configuration. So as a consequence, I can calculate the free energy variation, which is the sum of the internal energetic part or enthalpic part and second side, the entropic cost. I'm in a canonical ensemble here because I'm dealing with a system which is thermalized at temperature T. Therefore, if I take the expression before, the minus compensates, so I have 3 kT times R squared over 2NA squared, because there was this here factor 2. Up. So the increase of free energy when I go from a configuration that comes back to itself to an extended configuration has this form. And here we should stop a bit and comment. There are basically 3 comments we can make. The first one is this one. So we have something which is harmonic. When I pull on the string or the chain, I feel a recoiling energy, a restoring force or restoring energy, which is quadratic in the distance. So it's a spring. It's an harmonic interaction. So we have elasticity. The second important part is that it's 1 over n. So if you wish, I could rewrite this with an elementary increase of free energy divided by n. This is the increase of free energy if there was only one monomer, and I divide by n. So basically, I'm really taking springs, but I put them in series. So that the stiffness is really inversely proportional to the number of springs. So it's a series of springs. And the final comment I'd like to make is the most important one, is this one. The stiffness of the spring is called the spring constant. If I write delta F as K over 2R squared, K becomes 3 kBT over NA squared, or if you remember the definition of the end-to-end vector, this is my R0. So the spring constant of that elastic object is provided by kBT. So we are dealing here with a spring, thinking about energy here, but of entropic origin. The reason behind this, and this is an example which is very important for soft matter in general, the reason behind this is that what matters here, when you take your polymer chain and you extend it, mainly you are not dominated by forces. In this model, even there are 0 forces. But the fact that you are extending the chain and ultimately you are really putting all the monomeric bonds in a queue, in a line, you end up with only one microscopic conformation for the macroscopic one. So there is a very, very small entropy in that case. Whereas when you are completely coiled, you have plenty of conformation that allows you to go from one point to itself. You have many fluctuations that would allow that. And therefore, the system is not very happy when you extend it because it only has one microstate for the macrostate you're observing. So the recoil is purely entropic. It's just because on average, there will be plenty of conformation where you are not extended that macroscopically you don't observe that. And it transforms itself into a real spring. And when I say a real spring, I can tell you that, for instance, there are labs at ESPCI in Paris or at ENS in Paris where people basically take single DNA molecules. You can think about the group of Vincent Croquette at LPS ENS and Jean-François Allemand and David Ben-Simon, or you can think about the group of Ulrich Bockelmann at ESPCI. Basically, either with magnetic tweezers or with optical tweezers, they take a DNA chain and they extend it, they pull on it, and they measure a force displacement relation. And then they put proteins and they study the DNA properties related to biological processes. But what they measure is really a recoiling force or restoring force, sorry, related to KBT. That's a fact. So it's a really important understanding, and it will have biological implications, of course. All right, so now let's take an example. We know that the stiffness is this one. So let me change again gears. All right, so we say that delta F is equal to K R squared over 2. And so we can calculate a force here by simply taking minus the gradient of that potential. Okay, this is a conservative force that appears here. And so we end up with K R, if R is the vector, with the minus here. All right, and so provided the fact that we know K, which is KBT over R naught squared, with a minus, we end up with this. So the magnitude of the force is 3 kBt R 0 squared times R. I don't need to put that. It's just the magnitude. And so it goes like 3 kBt the extent over NA squared, if I put back my parameters. So now the question is, let me take an elastic material. It's full of polymers. It's fabric materials with polymer chains. I hang it at a wall, and then I put a mass. So there is gravity that is creating a force. So I'm really putting my elastic material with hanging mass. And then I come with a heater, that's a lighter, and I just heat the temperature. I increase the temperature around the system. What will happen? Well, if I increase the temperature, it means I increase that quantity. But those are constants. So it means if the force is constant because the mass is constant, it means this guy has to decrease. So when I heat up an elastic material, it will tend to contract. This is a direct signature of anthropic effects and not energetic effects. Because normally, if you take, let's say, a metal, any crystal, and if you heat up the crystal, it will dilate. You will start to explore in your spring constants in your crystal, you will start to explore the anharmonicity of your potential of interactions, and therefore you will have dilatation, expansion. This is the stuff you will notice on every material. When you heat them up, they increase in size. But not soft matter-like materials, not polymeric materials, not fiber like wood, necessarily, depending on how they are made, because those are driven by entropy. And so when you heat up, you shrink. That's the opposite. All right, so let's finish by providing orders of magnitude that are relevant to biology. Point number 5 is if we are at the microscopic scale and we want to significantly elongate the molecule. So we want to go from a situation where the molecule is like that, let's say, to a situation where the molecule is a bit longer. With a typical, let's say, extent, which has doubled, for instance. This is reasonable to estimate that a notable deformation in when the object double its size, okay? So what is the typical force needed to do that? Well, we have everything here. It's 3 kT over Na squared. So multiplied by R naught. and this is R0 squared, that guy. So we end up with 3 kt over R0, which is square root of n times a. And this is the Boltzmann constant. Let me put orders of magnitude here. So we have 3 kBT at room temperature, which is 300 Kelvin, is typically 4 to 5, 10 minus 21. Square root of n, we said it's 10 to the 2. If we take, let's say, 10,000 monomers as a length, and A was 2 angstrom. All right, so if we forget about the prefactors, we have 10 minus 8. This is, let's say, this is the piconewton range, or a fraction of that. In biology, forces are in the piconewton range. Okay, this is an order of magnitude. This is the order of magnitude you would need for DNA to uncoil, for instance, okay, in terms of force. Okay, this is one number, but in order to understand if it's big or small, we would need another typical scale. And another interesting scale is what is the scale needed, the force needed, if you want to break one single monomer. Let's say you want really to break the connection at the middle. To do that, the typical force will be, let's say, the bond energy, the energy of the bond. So for instance, if you have a covalent bonding, you know that it's in the electron volt-like scale, divided by the size of the bond. This is how you construct a force, an energy divided by a length. And so you can take, let's say, 1 electron volt. Think about the hydrogen atom, which is 10 electron volt, typically for the magnitude of the link. Well, let's take this unit. And A, we said it's angstrom. All right, so this is 10 minus 19 in joule, and this is 10 minus 10 in meters. So this is 1 nanonewton. So you see, you have piconewton here, you have nanonewton here. So the force needed to extend a bit the chain is 1,000 times, that means much smaller, than the force needed to break a bond. So there is margin before we reach the point where we break everything, okay? And now you have orders of magnitude to compare things. All right. So it's soon the time for a conclusion. And this is the final question. We would like to just summarize what are the limitations of that model, because it's interesting. Now we have the probability of a certain extension, so we have all the statistics we need, and we could calculate macroscopic quantities such as the force I need to, for instance, elongate a DNA molecule. The limitations are pretty clear. First, we assume that there is no energy contribution. Energy contribution is missing. Why so? Well, in fact, the monomers, they cannot overlap. There will be a strong repulsion by the nucleus cloud, right? So when the two monomers are close to each other, there is a barrier. So they cannot overlap. So already, you cannot freely rotate, but the past matters in your random walk. You have to remember that there is something or some friend who's already occupying the space. So this will be repulsion. You also have some interaction between the monomers. Very far away, 2 units of the same chain, they will talk together with van der Waals forces, basically. And so, in most general cases. And so they will attract each other. So far away, they will attract each other. Very close, they will repel each other. So you already have 2 interactions. More than that, this chain is not living in empty space. You put this polymer chain either in a solvent or even worse, with plenty of other molecules, either polymer chains, but also other molecules, charges, and so on and so forth. So in fact, the picture is that you mostly, in real cases, have a chain which is made of units. Those units, they talk to each other distantly, they talk to each other remotely, but they also talk to other objects, eventually also other chains. So you see, the picture is in fact much more complex than the one we provided you today. Nevertheless, you will see that it is first already providing us many interesting aspects about polymer physics at equilibrium. We already have some orders of magnitude, which is a good start. We already know the typical distributions. But more than that, you will see that it happens that there are some cases, and important ones, where in fact, those interactions, they all cancel out magically in a sense. And so at the end, the Gaussian picture works in several interesting problems. I mean, actually work, practically speaking. And we will discuss that later for the next tutorials. All right, so I'm done now. I'm really curious about what you thought, because for me, it's the first time I teach like that. And normally we have thousands of questions during my tutorials. I mean, I'm just chatting with you, I'm interrupted, we rediscuss the points, everything is not clear, so I just have to do it again and again. And here it's completely impossible, and you seem very silent. So can you please provide me some feedbacks by emails on the pace? Was it fast? Was it slow? Did you get the main message? And also, if you have ways of improving, I mean, even the writing or the appearance of that, because I don't know if it's clear to you. Finally, I've recorded that session, so I can put it online if you want to go back to a specific point. Of course, please keep this for you, because this is just an informal way of discussing. It's not meant to be publicized anywhere. Finally speaking, on the Dropbox folder, you will have access to all the documents. And really, I encourage you to read the articles, the abstract, the names, the date, where the research was done, for instance, because it will give you the landscape. It will start to build your own picture of who did what and where and when, so that at the end of this year, you might be more in a situation of saying, oh, this is a good question for a PhD, or this is another good question for a PhD. And you need to do that generally for all your courses. So please, if you don't have time to prepare the tutorials, which is obvious to me, still, when you are in the subway or when you have spare time, just scan the articles, look at the titles, look at the keywords, and try to make a picture of what is important inside this without reading the details. Okay, so with that, I will thank you for your attention, and I hope you will have comments. I will answer to them mostly next week, I think. Thank you very much. I'm waiting for any questions if you have some. All right, so if not, I thank you for your attention, and let us discuss by email and next time.